Right. So morning, everyone. Week 3, lecture 1. Yeah. Now we're down into the deep of things. So your lab is due tomorrow, I believe, 10 a.m. And the next lab is already out, right? So this second lab will actually look at HTTP in a lot more detail. So I think we've given you some packet captures, essentially a trace that captures some HTTP traffic, and we ask you to use Wireshark to observe the packets and then answer some questions. So that should sort of help consolidate some of the concepts that you've learned last week. What I'll do is, in fact, I would strongly encourage you to run a live Wireshark capture as well. Maybe not today because I've got a lot to cover, but maybe on Wednesday, I'll do a quick demo of a live Wireshark capture. That's something you can do in your own time just to explore how all these protocols actually behave, right? Okay, so when it comes to HTTP, we pretty much covered most of it. The basic protocol, as you saw, is fairly straightforward, but there's a lot that goes behind to sort of improve its performance. So we talked about the page load time being an important metric and how we can use various ways to improve that. So we looked at this whole concept of persistence and pipelining. In fact, that's what's stated here. So if you recall, what HTTP 1.1 does is it establishes one single TCP connection between the client and the the client and the server. And then all objects that are part of that particular web page will be fetched on that single TCP connection. And in fact, once the index page is downloaded, the client would already know how many objects are to be fetched. So all those requests could be pipelined, essentially sent back to back in the hope that the responses would come back to back, right? Then we talked about web caching and how caching can help. We talked about cookies and how that allows us to do a lot of interesting things. But then we also looked at some of the privacy implications of that and how third parties can actually track our web browsing behavior, right? So that was quite interesting. And throughout the slides, in fact, particularly in the cookies part, I've left some links for you. So feel free to explore that in your own time. Of course, some of those explorations are not part of these course. You won't be asked questions outside what we cover here in the lectures. Okay, so there's one last bit here remaining about HTTP. This is more sort of forward-looking, and in fact, this highlights one of the problems with HTTP 1.1 in that even though we are using pipelining, the server will still respond in a first come, first order in terms of the requests the server receives, right? So if you have, in fact, it's best illustrated through the next slide here. So if you look at how HTTP 1.1 works, is that if you have, say, 4 objects there, as you see in this slide, and let's say the first object is a very large object, say a video file, and then you have 3 smaller objects behind it, then the server will service them in the order in which they're requested, right? So as you see here, the first object takes, since that's the first one that was received, the server will spend quite a bit of time serving that particular object, and then it can move to the other objects, right? So this is a little problematic in that all these small objects then need to wait for this big object to come by. And which means very likely, if assuming some of these objects are images and other stuff on the web page, then your browser can't actually render anything. It has to wait for this big file to come through before it gets these smaller objects, which also make up a significant part of the page, right? So the second iteration of HTTP, HTTP2, which is kind of kind of slowly getting adopted quite sort of widely. It tries to reduce this delay, particularly when you have these multiple object requests, right? So of course it does a few other things which we won't get into. Some of the method status codes, all that are the same, but what it primarily does is it allows this change in the transmission order. So in fact, you can also specify a priority. And what it will do is it will break up this object into frames and then schedule the frames to mitigate this problem, which was shown on the previous slide. This problem is often referred to as head of line blocking, right? Because you have this one object that you're trying to, which is very large, which is blocking the other objects behind it. So that's why it's called head of line blocking. So the way HTTP2 would address that specific problem, again, going back to that same example where you have a large object followed by 3 smaller objects being fetched, it would break these packets into smaller frames and then interleave the frames essentially. So something like that, right? And you notice here that the subsequent objects are so small, they can virtually be sent in 1 or 2 frames like you see here. Which means the subsequent objects, as you see, object 1 just made up 1 frame, object 3 has 2 frames, object 4 has 1 frame. So you already see object 2 and 4 were already received by the client in this first frame, effectively, first round robin of the 4 frames, right? And then the remaining frames of object 1 can come through. So effectively, the client can receive all these objects which were blocked by that large object. Of course, there is a trade-off there in that the first object is delayed slightly, but given that the size of the subsequent objects is small, it's not really a significant impact here, right? So this is widely used in the second version of HTTP. So yeah, that was all that I had left from the HTTP part. We went over these quizzes. I have added these into the slides, so you can have a look. The last bit remaining from last week's slide set was email, which is the next and perhaps a fairly widely used application as well. Now, there's not a lot to email, so you'll see my coverage here is going to be fairly small, just a few minutes. Because there are some parallels already with HTTP, as you'll see, right? So email, of course, the application contains a lot of components. We will, of course, just focus on the protocol SMTP, which is mainly used for delivering email from between mail servers, right? So, of course, email also entails the user agents, which are the clients that you use to write up your email. So be it, say, the mail client on your MacBook, Outlook, or whatever other clients you might use. So those are effectively your user agents. So they allow you to read and write email, compose emails, do all sorts of fancy things, right? So that's the sort of front end essentially of email. The back end effectively is made up of the mail servers. So anytime you subscribe to an email service, you're allocated an inbox, essentially a mailbox on that particular mail server. So that's kind of designated by these blocks here. So for example, all of you have a UNSW email, which is your ZID. So each of you has a mailbox on the UNSW mail server. So do I, being a staff. Of course, we might have other emails like Gmail, Yahoo, whatever. So we get a mailbox on each of those. And the mail servers are where all the outgoing, incoming messages get stored. And then, of course, your user agent can go and access and download those emails from those mailboxes, right? Now, the glue that holds everything together is, of course, SMTP. The name as the name indicates, it's Simple Mail Transfer Protocol. So that's actually used for transferring email between the mail servers, right? So yeah, there's a mailbox for all incoming messages for the user. Whenever you're sending a mail, again, it needs to sit in an outgoing sort of queue, and it will reside there until the mail server has successfully delivered it out to the recipient, and then it can be deleted, right? Of course, you can store a copy within your sent mail folders and stuff like that, right? So the SMTP protocol, again, if you look at the specific protocol, it again follows the client server model. So the entity, the mail server that's pushing out the email effectively becomes the client. The recipient's mail server that is receiving the email becomes the server in that particular interaction. Right? Email uses TCP, again, because it wants to make sure that the entire message is delivered in a reliable manner. The port number used is 25. Now that is the SMTP port number. There is now a secure version. I forget the precise port number of that. You can look that up, but just like HTTPS has a separate port number, so does the secure version of SMTP, right? Which runs over TLS, doesn't directly run over TCP. So before the email can actually be sent, the sending server, which is effectively acting as a client, will start off what's called a handshaking process. So there's a bit of handshake messages exchanged between the client and the server, then the actual message is transferred, and then the connection is closed effectively. Now, the way SMTP works is if there are multiple emails to be sent from, say, a particular mail, say, so the UNSW mail server to, say, the Gmail mail server, all those emails will be sent over that same TCP connection, right? Because it makes sense to send everything over a single TCP connection rather than setting up new connections each time. Now, again, email, in fact, dates way before HTTP. I think email was developed in the 70s. So the protocol itself is fairly archaic in that it, again, uses ASCII. So in fact, though these days mail servers will not allow you, but if for some reason you can telnet into a mail SMTP server, you can actually type these commands because these are just ASCII. So you can sort of interact with a real SMTP server. Now, of course, these days, normally you would expect system administrators to disable someone from just randomly telnetting into their SMTP servers, but that potentially is possible, right? Because the commands are all ASCII. There's a question, RFC. RFC is basically the standard. It stands for request for comment. So all open source protocols, all sort of publicly available protocols are specified in the RFC. So you can Google for RFC 5231 and you'll actually get the specification for SMTP. And if you wanted to, you could write your own SMTP server. You could write your own SMTP client as well. 587 is the secure port. Thanks, Taram. What is handshaking? I'll show you that in a minute. Just give me a couple of minutes. So this is the scenario. So sort of outlining the entire process. So let's say Alice wants to send an email to Bob. Alice opens up her user agent, writes the email. The email will go and sit in her outgoing queue, which is here, the outgoing queue for the mail server. The Alice's mail server will then set up a direct TCP connection with Bob's mail server, which is the recipient. Once the TCP connection is established, the SMTP client will, they will effectively talk to each other. And I'll show you the interaction on the next slide. And once that is done, the actual email is sent over the TCP connection, and then the TCP connection can be toned down effectively, right? So Bob, mail server, on receiving this email, will put it in Bob's mailbox, and then Bob can go and invoke his user agent to read the message, right? So remember, email is asynchronous, right? Unlike HTTP, which is synchronous, the client and the server are online at the same time. in email, the sender and the recipient don't need to be online at the same time, right? The sender can send the email anytime, and then whenever the recipient feels like, they can go and retrieve the email, right? So this is a real interaction. So mind you, this is not fake. This is exactly how the sending SMTP server and the receiving SMTP server interact. So this is the handshaking that I was referring to, right? So a greeting basically. So there are again specific codes which you can find in the RFC about which indicate different things. So this is basically the server just announcing its presence, the client saying hello. So this is again a specific SMTP command. This says hello, so pleased to meet you. So this is the handshake, and then the mail from, effectively telling who the mail is from. The server confirms, the server again confirms receipt, and then there's data, and then the actual email, and then there's a separate dot, a carriage return line field, dot carriage return line field at the end, which indicates this is the end of the message, right? And then quit, and that's it. So these are just codes. So just like HTTP has codes, similarly SMTP has codes, and these codes mean different things. So you can look that up in the RFC if you're interested, right? So just like in HTTP, 200 indicates all okay, and so on and so forth, right? Handshaking is basically setting up the TCP connection. No. So the TCP connection is established even before this happens, right? So the TCP handshake is separate, that happens. And then there's a specific application layer handshake, which happens. So this is not related to TCP. The TCP handshake has already happened. The connection has established. And then the server and client go through this handshaking. So there are some obvious similarities with SMTP. Both are using ASCII command response. Both of them use these weird status codes implying different things, and so on and so forth. The mode in which they operate are slightly different in that HTTP is a pull protocol, right? So the client is the one requesting the object, and then the server serves the object. SMTP is reverse because it's the sender who's pushing the email to the recipient. So in that sense, it's a push operation rather than a pull operation, right? Some other differences in HTTP, each object is typically encapsulated in its own response, whereas in SMTP, if you send multiple attachments, it will all go and sit inside one large application layer message. Mind you, that message will effectively get broken down into TCP segments and so on and so forth. But from an application perspective, it just creates this one huge multi-part message. And there are specific headers called MIME headers, which handle all these multiple objects and their encoding. Again, that's something we'll skip over. I already mentioned SMTP uses persistent connection. So if there's multiple emails to be delivered between two servers, it will all get delivered over a single connection. The everything needs to be 7-bit ASCII. So which means if you're sending non-ASCII stuff in an email, all of that needs to be encoded. Now, of course, there are various standards to doing this encoding. So the recipient's user agent can use the appropriate decoding method to actually render that particular object that's been sent, and so on, an attachment that's been sent, right? And I showed you how there's a sort of dot by itself, which implies the end of the message, right? Now, the actual mail itself has a separate RFC, a separate standard. So this is different from the interactions that you saw. So this is the actual email, right? So SMTP has nothing to do with this. There's a separate RFC, just like HTML, for example, right? So this defines the syntax. So in all your emails, you'll see there's a header and then there's the body and so on and so forth. So there's a separate standard for that. There's a question, what is CR? Yeah, that's carriage return line feed, right? So this is basically when you type in a new line, that's a carriage return line field. and then a dot and another carriage return line field. Right? What else? Right. So putting it all together, if you look at the way emails are delivered, there are actually multiple parts to this, right? Multiple interactions. So we talked about this delivery, the email that's sent from the sender's mail server to the recipient's mail server. But remember, the user agent also needs to send the email to the mail server, right? Now, this can be done in multiple ways. So if you're using a native app, then this email is very likely been delivered over SMTP. However, sometimes you might just use your browser, right? You might log into your Gmail using your browser, in which case this is of course happening over HTTP, right? Whatever Gmail or whatever mail client you're using, if you're using a browser, then this sending process would also take place over HTTP. Similarly, if you look at the retrieval from the user agent, so this also can happen over HTTP if you're again using a browser to read your email. If you're using a native client, say like Mail or Outlook or whatever, then this process takes place over a separate protocol called IMAP. Now you might wonder, why can't we use SMTP here? Can you think of why? Why cannot we use SMTP if you're, say, using a specific native client? Why should it be a separate protocol? Peyton, is that how I say your name? Yeah, that's a correct answer. This action is a pull action, right? You're pulling email. SMTP is a push protocol, so you cannot use a push protocol to do pull, right? So that's why we cannot use SMTP here. So if you're using a native app, there's a separate protocol called IMAP, which is used to retrieve email. It does a lot of other things. It allows you to sort of create folders and stuff like that and all that. But again, this is a separate standard. We won't really spend time on that, right? What is a push versus pull? Guys, I just covered that, right, in the previous slide. So a push is when the client is requesting something and the server responses. So like HTTP. SMTP is a push action because the sender is pushing the email to the receiver, right? So here we want a user agent to go and say, hey, I want to get the email, and then the server should send the email. So this is a pull action because the recipient is pulling the email, whereas here the email is being pushed by the sender, right? So this is a push action, that's a pull action. HTTP is not a pull-based protocol. I just explained that, right? Oh, sorry, HTTP is a pull-based protocol. It can push as well. I mean, yeah, in a sense, because if you think about this interaction here, I mean, this is the way this works is a bit tricky, right? Because you're writing the email, you're already logged in to that server. So you could, if you look at HTTP, you can also do push, because if you remember, there's this form. What was it? Put. So yeah, you're right in that HTTP also has a push mode in a sense, right? Because you have the put, post. These are actually push actions in a way, right? So yeah, it's perhaps not so strict in that HTTP does allow you to do that. So yeah, you're right. Okay. Okay. Yeah, a couple of quizzes and then we'll wrap up SMTP. So where was the quiz? Yeah. I think this is already active. So this is asking you, why do we have a sender's mail server, right? So in that whole interaction, why couldn't the user agent directly set up a TCP connection with the recipient's email? So just to clarify, if I go back. So what I mean by that question is, what I mean is, why can't this user agent directly set up a TCP connection, or maybe not there, but let's say here to begin with. So why cannot the user agent directly set up a TCP connection with the recipient's mail server and then send the email? Why do we need this in the middle? That's what the question is asking you. Yeah, I think these are all good points, right? I mean, we haven't yet touched on security, but these are the points I was looking for essentially. What if the recipient is not online, right? What if the recipient's mail server is not online? I mean, that can happen, right? It's not guaranteed. I mean, of course, typically mail servers are online all the time. But what if it's not online? What if something, the connection failed or the recipient couldn't receive the email, right? Because remember, the sender, you cannot assume that a sender will be online all the time, right? So we need a intermediary who's going to store this sending the outgoing email in case something wrong happens, right? And then of course some of the other security stuff is also important. So yeah, well done. Then similarly, why do we need a separate receiver's mail server? So here it's asking, can't the receiver run the mail server on their own system? So let me move forward. Let me activate this one. So effectively, it's asking, why do we need this, right? Why couldn't, say, the sender's mail server directly dump the email to the user agent? So while you're answering that, there's a question, is SMTP's push-only nature more as a result of the time of the standard is written? Not really, right? Because if you think about it, email is meant to be asynchronous. So given that it's the sender that's initiating the action, is inherently a push action. There's no requirement that from the email application's perspective that the recipient be online, right? So how could someone pull an email if they're not online? Because the email is entirely initiated by the sender without any assumption about the receiver being online. So I think it's not so much age, it's just how email is supposed to be, right? Also, if it was pre-HTTP, would mail clients have been written? Well, mail, people have been accessing the email through web for years, since the web came about, right? So that hasn't really stopped people from using Outlook or mail. So it's really up, I mean, it's a matter of preference at that, in that case, right? Some people prefer to use browsers, some people prefer to use native mail clients. So it just gives you flexibility, I guess. Receiver may be offline, may not be always online. Yeah, I think you've all nailed the answer, right? The primary reason is, of course, what if the user is not online? We talked about how email is asynchronous. So we cannot assume that the recipient has to be online. So we cannot just expect the recipient to run the mail server directly on their end system, right? We need some intermediary. And again, matters of scale come about, right? Because how inefficient would it be for each of us to run our own mail server on our machine when we can have a dedicated mail server which handles all of this? So all of those factors come in, right? And of course, security, which some of you are pointing to. Yeah, well done, everyone. Okay, I think that covers the slides from last week. So let me just quickly transition out. Okay, so let's get right into it. The rest of the lecture, we are just going to focus on DNS, given that it's a fairly important topic. So get ready. Of course, there's a lot of content here on the slides. There's a lot of content in the book as well. But if you're interested, you can also look up this resource, which will also go over the same things really. Okay, so DNS, why do we need DNS? Well, as you know, we as humans, we have different identifiers, right? So we have our name, our tax file numbers, ZID, passport numbers, and each of this has its own purpose, right? So from a uni's perspective, they often use your ZID as your identifier. Of course, as an individual, for me, it's easier to remember, say, your names, or it's easier for you to remember your friends' names rather than their ZIDs. I mean, it would be so strange for me to say, hi, Z53256 or whatever, right? That just wouldn't make sense, because for me, it's easier to remember, say, Daniel, Peyton, and so on and so forth, right? So the same thing applies in the context of computers, right? So as humans, it's easier for us to remember host names like Google, Yahoo, or whatever, rather than their actual IP addresses, right? Because if you remember, we talked about how all web domains, or for any service that you need to provide, has to be hosted on a server, and that server is uniquely identified by a 32-bit IP address, right? You might have already seen this when you were doing trace routes for your labs. It's effectively in the format of A.B.C.D. We break this down into 8 bits, and each bit is converted to a decimal, right? So of course, from a perspective of computers, they are better at dealing with numbers. So when you're writing code that runs, say, the software for client servers, or even some of the router code, the protocol stack itself that's run in Linux, all of that works well with fixed size IP addresses. Whereas for us humans, we deal better with mnemonics, like identifiers that we can remember. So clearly there's a need to map between the two, right? Because when we use when we are using the web, we always use names like that. And remember how we said before your browser can actually download a web page, it needs to set up a TCP connection. In order to set up a TCP connection, you need to provide, you as in your program, the browser program, needs to provide the IP address of the server when it sets up the TCP socket, which we'll look at next week. So clearly there needs to be a way to map between the IP address and the name, and vice versa. So that's where DNS comes into play. So DNS, effectively, if someone asked you what is the DNS, it is the yellow book, if you remember yellow books, where you look up someone's name and it gives you the phone number, right, for that particular service. So DNS is doing exactly that. You ask DNS, hey, can you give me the IP address for www.unsw.edu.edu? And then DNS will say, here's the IP address that's hosting that particular web server. If you say, hey, I want to send an email to salil@unsw.edu.au, your mail program will send a query to DNS, and DNS will say, hey, here's the IP address for the SMTP server for UNSW. And then your mail client will set up a TCP. Your sending SMTP server will send a TCP connection. You get the point, right? So what is DNS? It's actually a distributed database. Now, we will talk a bit about this, but clearly this cannot be done in a centralized manner. You cannot have one single yellow book, because clearly there's too many host names that can be managed by a single entity, and a single entity would be a single point of failure, right? So if that entity went down, DNS would go down, which would mean the whole internet pretty much goes down, right? So DNS comprises two things. It comprises the actual databases that implement the way in which these mappings are stored. So these servers are called name servers because they are sort of giving you mappings for host names. And there's of course a way to send queries and receive responses, right? So we've talked about application layer protocols. You've looked at some examples, HTTP request, HTTP response. So the same thing applies for DNS, right? We need a way for these name servers to communicate with each other, to send queries, to receive responses. So all of that is also part of the DNS standard. Now, if you think about it, this mapping is rather important. I mean, this is very fundamental to the internet. In fact, every month, you'll probably experience some outage. Sometimes, I mean, not all the time, but I think last month there was a small outage where Amazon and few other services went down for about an hour. And that was primarily because something went wrong in the DNS hierarchy, right? So anytime DNS fails, the internet pretty much stalls. So it is a very fundamental function that is necessary for functioning of the internet, or rather the applications, I should say. The core internet itself doesn't go down. It just, the applications running on top cannot get the mappings they need to set up the send packets, basically set up TCP connections or even send UDP datagrams. So in fact, it is actually a core function if you think about it, but the way it is actually implemented, it's being implemented at the edge of the internet, right? By the edge, remember we talked about how the internet is a cloud, and then you have these end systems running on at the edge. So you have clients, you have servers, right? So they all sit at the edge. So this mapping is actually done using clients and servers that are sitting at the edge. So there's a point here being made: when DNS is down, can you still access sites directly via the IP? Yes, you certainly can. But the problem is those IP, how do you get the IP address, right? So unless you have already found a mapping between the host name and the IP address, you're okay. If not, if the yellow book is not accessible, then you cannot get that mapping, right? So that's why if the DNS goes down, then the various applications cannot run on top of the internet. Okay, so yeah, the complexity is actually implemented at the edge. So this is actually a very clever way to do things, because if this mapping was done in the core, it would look very different and we would have all sorts of problems. So a bit of history here. Initially, all these mappings were actually stored, managed by a single entity. So these were all maintained by the Stanford Research Institute. By the way, here I'm talking of the late 60s, early 70s. So this is really old stuff when the internet was just some workstations in some research labs and universities, right? So the general public wasn't really accessing the internet back then. And in fact, these mappings were stored in a host.txt file in that particular directory in the workstations. And the workstations would very often go and request an update of this file, right, from the Stanford Research Institute. And say if you wanted to change your IP address for a particular server that you're hosting, you would have to then send the update via email. And then someone at SRI would actually make that change and then send the updates to everyone else, right, as you see here. And in fact, this gentleman, John Postel, was responsible. He was basically Mr. DNS at that time, right? He was managing DNS at SRI. And clearly, as the internet started growing, this was a problem because, first of all, it was hard to come up with names that were not unique. I mean, people started using the same names. There were all sorts of inaccuracies in these host.txt files. And in fact, John Postel, there was an incident, you can read it up here. I'm not going to spend a lot of time on that. He actually, as a sort of rebuke to the White House, who were trying to encroach on the internet, the government in the US, he sent some wrong updates in these host.txt files, which led to certain parts of the internet not being accessible. Just to make a point, I mean, he was not trying to do any malicious things as such, but clearly that again raised eyebrows because it meant one single person could actually bring down the entire internet. So obviously a centralized approach doesn't work because it's a single point of failure. The other question is, where would you host this? Because the internet is now global, right? You can't just say, okay, I'm going to host this central yellow book in the US, because then that's far for everyone else. How do you maintain it? How do you manage the traffic volume? So clearly a centralized approach doesn't work, right? And if you look at DNS itself, it's actually providing a lot of services. So of course, the basic one is what we always talk about, and we'll pretty much spend a lot of time on that, getting a mapping from host name to IP addresses. But it also does a lot of other things like mail server aliasing, because remember, for example, UNSW has its own web server, www.unsw.edu.au, but we all also have z blah 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 at unsw.edu.au mail addresses, right? Which means there's a mail server for unsw.edu.edu and there's a web server for unsw.edu.au. So which means we should have different mappings, because they may or may not necessarily be the two servers. The actual programs may not necessarily be hosted on the same machines, right? So we need a separate entry to take care of email. So as you'll see later, there's a separate MX entry which takes care of email. And the typical entry that we will talk about is called a type A entry, which maps a web domain to a IP address, right? As you'll see later, a lot of servers are replicated because it's a very bad idea to just have a single machine host any server, because if that machine goes down, then your server pretty much goes down. So almost all services, be it web services, be it mail services, will always be hosted on multiple IP addresses, and DNS can be used to distribute the load, right? Because if you're, as you'll see later, when DNS responds back with a mapping, it will actually send multiple mappings, right? So if, let's say you have got 3 servers, so in your response you would get back ABC. So what DNS could do, it could keep reshuffling the order of this. So for the first query, it might put A at the top. For the second response, it might put B at the top. So it will effectively cycle through all your IP addresses and distribute the load, right? Okay, there's a few questions here. Have a list of common website IP saved. Yeah, that's not very effective, right? Because that would mean what happens if your IP address gets changed? So, I mean, we cannot really live without DNS. As you'll see later, there might be various reasons why you might want to change your IP address. You might want to update your system or whatever. So we need a way where we can do that effectively and have this level of indirection that DNS provides, right? What is FTP? FTP is a protocol called File Transfer Protocol. It's basically used to transfer files, as the name suggests, right? Okay, so the goals are as follows. So we want to be able to create names that are not conflicting, because we can't have 2 domains using the same name. So the domain names themselves should be unique. It should be scalable in that we should be able to have many names. We should be able to do updates if required, because these mappings need not necessarily be fixed all the time. For various reasons, you might want to change how you're setting up your services. Say initially you had set up your own server in your physical hardware, then you wanted to outsource this to a web hosting service. So it should give you the flexibility to make those changes. And the most important thing is it should be completely distributed, and the administration of this should be autonomous. So as you see later, if I'm managing my website, I should have complete autonomy over how I set up my servers. And this should be, it should be possible for me to make these changes as and when I please. And at the same time, I do not need to worry about similar mappings for other domains, right? So I only take care of my domain, say, I don't know, salilkanere.com. I don't need to take care about UNSW. I don't need to take care about CNN. They manage their own, right? And I don't have to track all those updates, as you'll see later. And of course, this it must be highly available, in that DNS cannot go down, as I already hinted, because if it goes down, then it becomes a problem. And the lookup should happen very fast, because you may not even realize when you're accessing any website, we talked about how a TCP connection needs to be established, but before that TCP connection needs to be established, your browser needs to obtain the IP address of the host name that you have typed in. So this requires it to send a DNS query, right? So this DNS lookup really has to happen very fast, as fast as possible, because otherwise the user is going to experience delays, right? Who is responsible for name servers? I'll talk about that. Of course, you're trying to jump ahead, Tim. Just give me some time. As I said, we'll be talking about DNS this entire lecture. So we'll get into all those specifics. There's some cost when making an API call. Yes, certainly. So there is a API call that all the programs that we run make. It's called get host by name, and that initiates a DNS query, right? As we'll see later. So yeah, we'll get into all these questions. Please just be a little patient as we sort of peel the onion here when it comes to DNS. So there are actually three intertwined hierarchies. So the first one is the actual namespace itself. So how do we organize the naming of the domains? So that also is hierarchical. As you already see that www.unsw.edu.au, right? So you already see that hierarchy, unsw.edu.au, right? Then we have the administration itself, which is hierarchical. So who's managing what part of the namespace is also hierarchical. And then the actual servers that are holding these records are also distributed. By distributed here, we do not mean that the same database is replicated across all the servers. In some cases it is, but by distributed here, really what we mean is different. You can imagine the yellow page, right? You're keeping different pages on different servers. And some, of course, some of that gets replicated, but effectively, rather than storing the entire copies of the yellow pages everywhere, we kind of tear it up and keep these pages in separate servers, right? So the namespace hierarchy is depicted here in this tree structure. So we start at the root, and then we have what are called top level domains. So .edu, .com, .gov, .mil. The country ones, we also have, of course, AU here, and so on and so forth. And there's a lot of new ones that have been recently announced. So there's weird TLDs now, like .tv, .io, .whatever. I mean, you can find heaps of them these days. But so those effectively are the top level domains. Then below that, we have the organizations. So as an example, Berkeley is a university in the US. So it sits under EDU. So below AU here, we have, again, EDU. There might be others. And then below that here, we have UNSW effectively, right? So the similar sort of mechanisms would work. And then under Berkeley, let's say, again, this is fictitious. I don't necessarily know if this is true. You might have a Elec and computer science department. You might have another department called SIMS. And then under EECS, you might have another domain, say instrumentation or whatever, right? So as you see here, this hierarchy can go down effectively. It can go down. I think the limit is 128, though you would be far-fetched to see real host names that have like 128 levels of hierarchy. Typically 4 or 5 are fairly typical, right? But what this also means is name collisions are fairly trivial to avoid, right? Because when you're setting up a university, you need to go to EDU, and then EDU will check what are the names of the current universities. So you can't have another university wanting to be Berkeley, right? Because there already exists a one called Berkeley, right? And then within Berkeley, since the administrators who are managing the Berkeley network, they know there's an EECS, you cannot have another EECS, right? So effectively, this ensures that you cannot have a clash of domains, right? So something like EDU and AU are both TLDs. Yes, they are all TLDs. All of this is basically TLDs. Google.hello.com would belong to hello, not Google. Technically, yes, but I'm pretty sure Google would not allow you to do that. They are pretty aggressive about these sort of things, right? How are TLDs like EDU and Gov protected? I'm not sure what you mean by protected here. If you mean the actual servers, well, as you'll see later, there are professional entities that manage these TLDs, right? So it's not some geek in a garage managing EDU or some geek in a garage managing Gov, right? There are designated entities who actually manage these. So they make sure that these are all managed in a protected manner. So continuing on with the hierarchy. So this is, of course, the first hierarchy, which is the namespace. The second hierarchy is the administration as to who actually administers what part of the namespace. So of course, I'll talk a bit more, but each of this is managed professionally. There are separate entities that do that. But within an organization, then it's up to the people managing the network resources, how they want to split it up. So for example, you might have the geeks in Berkeley who say are from the computer science department. They might say, hey, we want to manage our own domain, right? So they may talk to the central IT at Berkeley and say, hey, give us permission to manage our own namespace here, and you can take care of the rest for the other departments, right? So it's effectively each of these becomes a zone, and then each zone is effectively managed by an administrating authority. So as it says here, the UCB central IT might take care of everything like that, say berkeley.edu, sims. And then EECS might control everything under EECS, right? What did I say about not having two EECS? Well, I mean, why would, if another department went to Berkeley, another department, and say, hey, I want to create EECS, obviously Berkeley is not going to allow that, right? Because it already has an EECS subdomain. Who manages .tv.io? I'm afraid I wouldn't, you'll have to check that up. I don't remember all these things. There are obviously separate, is TV a country domain? I'm not sure. You can look that up. I wouldn't know specifically about, but clearly there will be entities that are designated to manage each of these, right? So these are the most common ones. Of course, there's plenty others. There's hundreds of TLDs these days. These were the old traditional ones, but for various reasons, the ICANN, which manages the naming for the internet, they've allocated a lot more TLDs these days. So the hierarchy actually starts at the root. We kind of missed root here, but if you look up any real, oops, sorry, what happened? Okay. If you look up any domain, right, there's actually a final dot at the end. So that effectively becomes a root. It's not actually shown and we don't type it, but there's a final dot at the end. So that becomes the root. So these are absolutely at the top. These are called root servers, and their locations are actually hardwired into the other servers, and I'll talk more about root servers in just a minute. Below that, we have the TLD servers. So these are the .com, .edu, and so on and so forth. All of these are managed professionally because we have to be careful on how the domain names are actually assigned, right? And then right at the bottom, as you saw in that example, we have what are called authoritative DNS servers. So these are the entities that store the mappings. These are, for example, in Berkeley, you saw there, Berkeley manages its own mappings, right? So Berkeley is responsible for maintaining those DNS servers, and these are called authoritative DNS servers. So these are the ones that have the actual mapping. So as you saw there, each server is sort of storing a small subset. An authoritative DNS server has the actual answers because, as the name suggests, they are the authority for that name server for that particular domain, right? And then the question is, how do you navigate this mapping if you want to actually resolve a particular query, right? So you start off at the root basically, and then you keep moving down till you get an answer. So I'll quickly show you this in this slide, and I'll revisit this after the break, right? So effectively, let's say I'm trying to find a mapping for this domain, right? robot.cs.washington.edu, right? And let's say I'm sitting here on the CSE network. Let's say my machine is called Titanium. So for now, just ignore what this means. I'll talk a bit more about this, but this is effectively an entity which will be sending out the query for me, right? So let's say I'm trying to access this website. So my machine sends a DNS query to this local name server. Let's imagine the local name server has no clue who to ask. So what it does is it goes and talks to the root name server, right? The root name server sees that the first part of the domain is a .edu. So it's going to tell my name server, hey, go and talk to the edu name server, right? Because it's a .edu address. So then I go and talk to the edu name server. The edu name server looks at the next part of the domain. It sees this Washington University, washington.edu. So it tells me, hey, go and talk to the Washington name server. It might have the mapping that you're requesting for, right? So then I go and ask Washington, and let's assume in this case, Washington has the mapping. So then it's going to respond back with the actual IP address for this, right? So again, this was just a quick peek. I'm going to talk a lot more about this resolution right after the break. Right? So let's take a break, and then we'll start looking at exactly the details of all of this, right? Let me show you my silly meme for the week as we go to the break. So this is basically what DNS does. Okay, so let's take a short break. I'll pause the recording and then we can return in. Okay, we are recording again. So let's start looking at the actual details, right? So I just gave you a high level view. Let's now sort of peel the onion and get right into it. So the root name servers are the starting point. So effectively, whenever we don't know who to ask, we always know we have the root servers to back us up, right? So you can imagine the root servers to be sort of a last contact of last resort, right? These are incredibly important. They must be online all the time. The internet wouldn't really function without the root servers. So ICANN is the organization, as it says there, the Internet Corporation for Assigned Names and Numbers, which is responsible for managing the DNS domain. In the olden days, there were actually 13 physical DNS servers. They were just labeled A, B, C, D, and so on and so forth. But clearly, this was again a problem because you couldn't just have 13 physical servers. So all of these are now replicated many times. In fact, even just in the US, there are now 200 physical servers that serve as root DNS servers, right? So there's a question about funding. I'm not sure where ICANN gets the funding. I presume they get some money from managing the domains and so on and so forth. So I guess I really don't know about the funding mechanisms, I'm afraid, where ICANN gets its money from. But I'm pretty sure it does get money from managing the domains itself, for which we have to pay a fee, right, in order to get the host name. Maybe there's some, I don't know, funding from the UN or whatever. I don't, I didn't think of that as a question. So I don't have a good answer on that. But in terms of the root servers, so here, for example, we could actually go to rootservers.org. Right. So this is the current state of the root servers. So you see there's, there's 259 in the US, 279 in EU, there's 30 in Australia. There's about 8 here, just around Sydney, right? So yeah, it's a fairly well-managed system because they have to be online all the time, right? Then below that, we have the TLDs. So these are responsible for .com, .org. Now, of course, some are more important than others, like all of these, all of the country ones, but then there are a few esoteric ones as well, right? So something like that. But clearly, all of them are managed professionally. So as I said, these are not just some geek sitting in a back office doing it. These are all responsibly managed. So for example, the .com domain is managed by Network Solutions, .edu is managed by EduCause, and so on and so forth. I believe .au is probably, I'd looked that up, I've forgotten now. So yeah, I think it's the Australian subdivision of ICANN. I forget what, APNIC, is it? Or maybe one of you can look it up, who's managing .au. So clearly these are all professional entities that are managing it. And then of course, right at the bottom, you have authoritative DNS servers, right? So these are essentially the organizations, the zones I showed you. So they are responsible for maintaining their own mappings, right? There's a question about multiple .com TLDs. So yes, typically all of them again would be replicated. I mean, even authoritative name servers are replicated. So obviously each of them are also replicated many times, right? Because without replication, we would have all sorts of problems. Now, one thing that's not shown there is Tim is saying AUDA. So that's the entity that's managing the .au. Thanks, Tim. I don't know what DA stands for there. So one entity that wasn't effectively shown there, and I hinted at that, is something called a local DNS server. So effectively, this is the entity in the client's ISP, which is responsible for managing the DNS queries, right? So this does not effectively belong strictly in the hierarchy. This is effectively what resides on the querying endpoint, right? So each ISP would have a default name server, and we are told of this name server when we actually get our IP address. So later in the course, you'll see that there's a protocol called DHCP, which we'll study. So this is what's used by your computer to obtain an IP address on your local ISP, whichever ISP you connect. And when you get that IP address, the DHCP server will also provide you with the name of your default name server. So all DNS queries generated from your machine are sent to this local DNS server. And then that local DNS server will manage the querying for you. You also have the option to configure your own if you have a different preference. So there are some open DNS servers out there that you can use. So for example, Google offers one, I think it's at 8.8.8.8. So if you prefer not to use your local name server, you could of course use one of these public name servers as well. There are some implications of that. We'll talk about that later. The client application. So anytime you have an application that sort of uses a host name, so like say your browser, and you need this mapping, the client app will trigger a system call called get host by name, which will then trigger this DNS query to be sent to the local DNS server. Now, the local DNS server also maintains a cache because if it's already has a mapping, then it does not need to go and request the mapping, right? So for that reason, and because the local DNS server is managing queries from multiple clients, it makes sense for it to cache these entries. So if you're requesting for an entry which it already has an answer to, it will reply immediately. If not, it will send out a query into the DNS black box, right? So effectively, it's acting like a proxy if you think about it. So now let me walk you through that process again. So let's say the requesting host in this example is at engineering.nyu.edu. And we are trying to resolve this particular address, gaia.cs. So that's the host name, and we are trying to get a mapping for that particular host name. Let's say it's hosting some web content, right? And I'm trying to access that here on this machine, and I'm located here. So my browser would initiate a local get host by name call that would result in a query getting sent out to my local DNS server, which is that. Now imagine this local DNS server has its cache empty. It's just been brought online. It has no clue who to ask. Now all DNS servers are configured with the IP addresses of root DNS servers, right? So this is a given. This is something that happens at startup time. So even though the DNS server does not have any other mappings, it will certainly have a mapping for one of those root DNS servers. So it will start off by querying the root DNS server and say, hey, do you have a mapping for this? Now, of course, I'm verbalizing this. We'll look at the precise formats of these query responses later. But just, I think it helps the explanations if I say it that way. So it asks, do you have a mapping for this? The root DNS server will never have a mapping for the actual IP addresses because that would just not scale, right? I mean, imagine keeping a mapping for billions of host names. So the root DNS server never has the actual answers that we are requesting. What the root DNS server's role is to redirect you to the appropriate TLD, right? So since this is a .edu, the root DNS server knows which TLD it should direct you to. So the query then it basically replies saying, hey, go and ask the TLD for edu, right? So then your local DNS server goes and asks the .edu TLD, says, hey, do you have a mapping for gaia.cs.umass.edu? Now in this particular example, it's sort of indicating that the mapping actually exists, right? So in this example, it's sort of implying the mapping exists. So it knows who has the actual mapping. So it, what it says is, okay, this is umass.edu, cs.umass.edu. So you should go and ask the computer science DNS server effectively, right? So this 5 is basically redirecting you to the computer science DNS server. You ask it for the mapping and then you get the response. Sometimes it may, let's say hypothetically, it doesn't have the mapping for cs.umass.edu, but it may have the mapping for just umass.edu, right? So there you might have an extra level of indirection where you are now being pointed to umass.edu. So in which case you would go and ask UMass, and then this would reply with cs.umass.edu, right? So you can have about 3, 4, maybe 5 levels of indirection before you actually get to the actual authoritative DNS server. So this is the one that has the IP address, right? None of them have the IP address. It's only the authoritative DNS server which has the actual IP address you're requesting for, because it is the authority for that domain, for the CS domain, right? And then finally, the local DNS server will pass on that reply to you, and then your client can set up a TCP connection with this machine and request the web page, right? Now these queries, this way of asking and responding is what's referred to as iterated queries, because each of these name servers is redirecting you to someone else, right? There's a different way to also do this potentially, which is called recursive queries. So the way this would work is this part is the same. Now in recursive queries, the root name server would take over the querying for you, right? So you ask the root DNS server, the root DNS server then goes and asks the TLD. The TLD then goes and asks the computer science DNS server, and then the responses flow back the exact reverse path. Now, I mean, this works fine, but do you potentially see a problem with this? It's kind of hinted on the slide, but could some of you elaborate? What could be the potential problem with these recursive queries? Yeah, I think some of you are pointing to the problem, right? Every query has to basically, I mean, imagine each query, the root server here is getting involved, right? So it's passing on this query, which means it needs to keep some state, because it needs to remember that when this response comes back, it should send it to the NYU name server, because the root DNS server may get millions of such queries, right? So if it has to keep a state for this and take over the querying process, it's going to put a lot of work on the root DNS server. And effectively, that's not what the root DNS server is designed. In fact, that's not even what a TLD name server should be doing, right? Because it would have to keep track of all EDU queries. So recursive queries are almost always disabled. The root DNS server will never support a recursive query. A TLD name server will never support a recursive query, right? So even though this exists, this is not widely used. This first step is actually a recursive query, if you think about it, even with the previous approach, right? Because what's happening is the local DNS server is taking over the querying for you. And then once the response comes back, you get the final answer. So this first step is always recursive. The rest are typically not recursive, right? Okay. Now caching, right? So caching again helps, because if you have the mapping stored locally, it means you don't have to go and send out extra queries. So the TLD servers are also typically cached in local DNS servers. So in that example, maybe if I go back one slide here. So imagine this local DNS server was just started up. And as we said, it initially has the root DNS mapping. Let's imagine it doesn't have the TLD mapping. So the first time it goes and asks the root DNS server, it would get back this response 5. Oh, sorry, this response 3, right? So this response 3 will contain information about the .edu name server. So the local DNS server will now cache the information for the .edu name server, which means any further queries for .edu can directly be sent to the .edu name server, right? It can bypass the root. Similarly for .com, similarly for .au, and so on and so forth. So all TLD mappings are typically cached, which saves that extra query having to go to the root DNS server. Now, of course, the bad thing with caching is things can be out of date, because if the IP address of a particular server changes and you have the mapping for the previous IP address, then you're trying to set up, say, a TCP connection with a host that is not actually hosting that particular service. So certainly there are some problems with that. The typical value for which, so each entry has a time to live. Most typical values of time to live are about 1 day, which means you can potentially have entries that are up to a day old. That said, web servers are not changing their IP all the time, right? So this is actually a fairly planned process. And as you'll see later, there's a rule of thumb that's generally followed when you want to change an IP address. And I'll talk a bit more about that in one of the later slides, right? So yeah, there's potential problems with caching, which we'll touch on. One other thing that often local DNS servers will also do is they will cache things that did not work, right? So sometimes people type in wrong domains, right? I mean, I'm sure some of you have done this, right? Where instead of cnn.com, you typed an extra M or you typed an extra N. Now this will result in a DNS query being sent out. Eventually, the query will never get a response because there's no such domain. Now your local DNS server, it will help it if it remembers this, because it's very likely some other users on that same network are going to make these mistakes. So by storing these wrong mappings, it's actually going to speed up the response process, because then it doesn't need to go and query for these non-existing domains, right? So this negative caching is also often employed by most local DNS servers. Now, how do the records actually look like, right? How do those entries look like? So they have a specific format. So these are called resource records, RR format. These are the most important fields in that particular resource record. So we have the name, the value, the type, and the TTL. TTL is basically the time for which this record can be stored in a particular DNS server, right? The cache, basically. So these are the name and value varies depending on the type. So the type A is the classic query we are talking about. So when you're trying to map a host name to an IP address, the name is the actual host name. So www.unsw.edu.au, and the value would be the IP address for that particular web server. NS is when the value is pointing to the authoritative name server, right? So if you go back to one of these examples, let's look at the iterative queries again. Let me clear out all my markings. Oh, sorry. Yeah, right. So this one, for example, oops, sorry, what's the pen? So remember we said, okay, the local DNS server queries the root DNS server, and the root DNS server responds back with information about the TLD name server. So this response 3 will actually contain an NS entry. It's going to tell you what is the name server that's managing the .edu domain. So if you look inside this query number 3, you will see a type NS record, where the name will be basically the .edu, and the value will be the actual host name of that name server that's managing the edu hierarchy, right? So that's where you see type NS records. CNAME is interesting. So this is what's referred to as a canonical name. So now normally you might be requesting for, say, ibm.com. But if you look at the actual name of the server that's hosting the IBM website, it's not actually going to be named ibm.com. It might have some weird name like that, right? And this really depends on how the web servers are actually set up within an organization. So the actual name is very likely going to be something weird like that. And of course, IBM cannot expect individuals to remember this. So it of course wants individuals like us to remember this, but then there has to be a way to go from this to the actual long name. So that's where the CNAME comes in. So this, in this case, the name is the alias. So that's the short form. And then the value will be this very long name that you see, right? And then finally, and again, CNAMEs are also used in CDNs. So this is something we'll look at. In fact, I'll show you an example in just a few minutes, right? So when you're offloading your hosting to a CDN, you would normally see that CNAMEs are used for that purpose. And then finally, we have a type MX record. So this is mainly for email. So this is where the value is for the name server, right? So as I said, with UNSW, we of course have a type A record for our web server, but we also have a type MX record for our mail server. So depending on which program is sending out the query, If it's a browser, it's typically going to request type A. If it's a mail clients will normally be requesting a MX record, in which case this entry gets sent instead of this one, right? Tim has asked a good question, yeah. So the NS value here, I said, is the name of the host name, right? But in practice, you would actually need to know the IP address. So if I go back, yeah, this one, right? So here I said this NS record should be the .edu name server, right? So be it a.edu or whatever. Now, in order to send this query, your local DNS server also needs the IP address, not just the name server. So Tim, you're right. But normally what would happen is, as you'll see later, when I show you an actual response, there will be an additional field in the response. And this additional field will actually hold the IP address as well. So that way you don't have to send out an explicit query to get the IP address for that name server. But that's a good observation. And yeah, that could be the same for CNAME. So I'll show you a response fairly quickly in just a couple of minutes. And you'll see that some extra information is also included, which allows us to save on these extra queries, right? So this is the actual format of the request and reply messages. Both have the same exact format. There's an ID field, which indicates just the identifier of the query. So this allows, when you're sending a query, it will have some ID. So the response that comes back will have the same value in the ID. So it tells us that this is the response for that query that was sent, right? Matches a request to a response, basically. The flags indicate what type of information is in here. So whether it's a query, whether it's a reply, whether the reply is coming from an authoritative name server, a recursion, and so on and so forth. The next 4 entries are fairly straightforward. It indicates how many questions are contained, how many answers, how many authoritative records, how many additional records. This is the questions that were asked. This is the answer. So that's the actual response. And you, of course, can get multiple records here because almost all name servers are replicated. So you always get back multiple responses. This is where some extra information can come in. So this can contain information about the authoritative server. For example, if this is being sent by, you might get the information about who's managing the authoritative name server of the query that you're after. And some additional information, as I just pointed out to Tim, this can have some additional information which may save you some extra queries. Okay, there's a question. What is the difference between root DNS server and authoritative DNS server? They are very different. Martin, you might want to go back and look up this slide. So the root is basically just redirecting you to the appropriate TLD, right? So root is right at the top there. If you don't know who to ask, you ask the root, and then the root will point you to the appropriate TLD. The authoritative name server is the one that has the actual mapping for a domain. So in this example, it's say gaia.cs.umass. It could be cse.unsw.edu.au, right? So that's the authoritative name server that has the actual mapping. Okay, so this is an example. This is what, in fact, you'll be doing in your labs next week. Your next week lab is entirely focused on DNS. So there's a particular command line utility called dig, which initiates a DNS query. This is showing you a screen capture of something I did earlier, where I queried for the mapping for www.oxford.ac.uk, and this is the response I got. So up here, you see some headers. Basically, it's saying it's a query. It indicates the ID, certain flags. This is actually showing you the header of the response that I got back from my local DNS server, right? So this is actually the local DNS server that sent me this response. So my query went to the local DNS server. The local DNS server then sent it out into that hierarchy. It got the response back, and it's now sending back the response to me, right? So you notice there are 4 records in the answer, 4 records in the authoritative, and 6 records in additional. What else? So the query is of course a type A query because that's what I requested, right? You'll notice here there are 4 servers coming back. So this, as I noted earlier, most websites would be hosted across multiple servers for redundancy. And typically what DNS does, it will keep shuffling this order. So when I send the response, maybe I got this order. If you send a response, you might get a different order, right? So they try to sort of do some load balancing because very likely my client will first pick this server, the first one here, right? So your client might pick a different one if the order was different. This here is telling us what are the name servers for this domain, right? So these are sort of the 4 name servers for that particular domain. This down here is additional information. So this is actually telling us the IP addresses for these name servers, right? So what this means is, let's say not in this context, but in another context, you wanted to actually query these name servers. Now, if you didn't have the IP address, say for DNS 0, and you only had the name, you would then need to send out a query to get the IP address and then send a query, right? So very often you'll find this extra information in the additional section, where if you're being told what are the authoritative name servers, you would also receive their IP addresses. And again, like here, you see the authoritative name servers are also replicated. So a rule of thumb is to at least have 2. Many organizations will have more than 2, just because you don't want a scenario where your authoritative name server goes down and then no one can access your mappings, right? Did DNS infer it was a record because the host name was, yes, that's correct. So the default, in fact, I believe the default option, yeah, because it's a www, right? So it's inferring this is a type A. There's a way to send a MX query where you might be asking for, say, the SMTP server for oxford.com. I think there's a flag, I forget. Maybe it's .m or .mx. You can do a man dig and you'll see all the options you can actually give. And in fact, in your lab, you'll be doing all these sorts of experiments, right? Oh yeah, good point. I missed that. So notice here, there's a 4 A's. So that actually stands for IPv6. So you'll notice this address is different in a different format. IPv6 addresses are represented differently because they're 128 bits long. Right? Sometimes you might even get AAA 4A addresses here. Okay, now the question is, how does the authoritative name server actually create the entries, right? So imagine you are a startup. You've started a startup called Network Utopia. You want to set up your web server. You want to set up your mail server. You want to have all your employees have email addresses at networkutopia.com and so on and so forth. And you also want to have a web server that's hosting your web page. So what do? Well, you first need to register the domain, right? So you need to go to some provider and you need to tell them, hey, I want to buy this particular domain. They're going to check if this domain is valid, if they can give it to you. You pay a fee, you get the domain, right? Now, what you next, and let's say you're managing your own servers, right? So you're physically setting up your own servers and managing it. You're not going to outsource it, right? So what that means is the first thing you now need to do is you need to tell the .com TLD that, hey, I've set up this domain. And if someone comes asking for my particular domain name, can you please redirect them to my authoritative DNS servers, right? So that's something that you first need to do, because if people are going to access your domain for the first time, they're going to, since it's a .com, they're going to go to the .com TLD. And then the .com TLD needs to know who it should redirect to, right? So what you should be doing is you should be setting up at least 2 authoritative name servers, a primary and a secondary one. So let's say DNS1 is your primary one, right? So you set up an actual server that's hosting this software, basically that's running a DNS name server. And in that software, and what you need to do is then tell the .com TLD that, hey, please insert these two records, right? So this is my name server, basically, that's what you're saying. And this is the IP address for my name server. So if someone comes looking for networkutopia.com, please send them these two pieces of information. So then they know who to ask, right? What this means is then you physically need to set up a DNS server at that IP address. You need to run the DNS server software, basically, which means if any time someone comes and queries this particular server, you then provide the actual type A record, or for that matter, the type MX record for the servers that are hosting your web domain and your mail server, right? So for the sake of simplicity, let's just say you're hosting your, this is a long one, 212.212.212.5. Now, mind you, it could very well be on the same machine, but just that confuses people. So I'm just going to use a different IP. And then let's say for your mail server, you have a .6, right? So that would be the type A record for your web server. And this would be the type MX record for your mail server. And these two records then need to go and sit inside this IP address. So in that particular DNS software that you're running, you need to create these two entries, right? And similarly, you would set up another one at .2, 212.212. So that would be your secondary. This was your primary, this would be your secondary. Both of them would have these entries, right? Which means when, let's say you tell your friend, hey, I've set up this web domain, and let's say that your friend goes and types this in, their browser is going to first go and talk to .com. .com is going to redirect them to one of these two machines, either the .1 or the .2. And then their browser is going to query that and then obtain this mapping and then view your fantastic website, right? So that's how all of this fits in, basically, right? Okay. Okay. Just grab a sip of water. There's a question, when you run a ping or trace route on a host name, will it resolve the name before the ping trace begins? Yes, that's correct. So when you type ping www.google.com, that would first generate a get host by name lookup to get the IP address, because ping uses ICMP and it needs to know, which is encapsulated in an IP datagram, and you need to tell the IP address of the machine you're trying to ping. So when you're executing ping, that also generates a DNS lookup. And then even traceroute, right? When you're using traceroute, that also first generates a DNS lookup. Is it possible to traceroute the DNS lookup path? Yes, you can. I mean, that's going to show you the path towards the, so you'll have to traceroute to that particular IP, right? So you'll have to get the IP address or the host name of the name server, and then you can traceroute the actual path towards it. It's certainly possible. Okay, so going back to my example is, yeah, so the .1 and .2 are the authoritative DNS name servers, right? And .5 and .6 are for these two domains. Now, again, I said this was just, in reality, all of these could be host. You probably don't want to host everything on a single machine because that defeats the purpose of redundancy. But if you really wanted to, you could say, have your web server and the primary name server on the same machine, though I think that's a bad idea. You ideally want everything separate, right? And as you saw in that response, everything was indeed separate, right? They're not using the same servers across this, just because you don't want one server going down, bringing down large parts of your ecosystem, right? Updating DNS records. Okay, so earlier I talked about caching, right? And I said that typical values for TTL is about 1 day roughly, right? So which means once someone has got your mapping, they're going to have that mapping for a whole day. Now, what if you want to make a change, right? Let's say you're unhappy with your web hosting service, you want to change over to a different web hosting service, which will invariably means you're changing the IP address for your web domain. So how do we manage that? So the general rule is as follows, right? So what you do is, this is again planned, right? You don't do this, you don't just get up one morning and say, hey, I want to quickly change my IP address. Sometimes there might be a genuine reason if something crashes, but in most instances, this is all very well planned. So what you might do is say, you know that tomorrow you're going to make this change. So you record the current TTL value. Let's say it's 1 day. Then what you do is you change the TTL for all your records to a very low value, right? You change it to 30 seconds. So which means from this point on, when you made this change, from now on, your entries are only going to be mapped, only going to be stored for 30 seconds. That's it, right? From this point on. Then you wait for the previous TTL. So let's say this was 1 day. So then you wait for a whole day, which means all the previous cached records will then get cleared out by tomorrow, right? Because now we have changed the TTL, which means for the past 24 hours, people were only caching your record for 30 seconds. So basically they were just disappearing like that. Any previous records have now been purged. Then you change your IP address, wait for a little bit, and then increase the TTL back to 1 day, right? So this is the rule of thumb basically, right? That when you're planning for a change, you reduce the TTL to a very large or small value, wait for that previous TTL period, then increase it back, and then you're all golden, which means at that point, it's very unlikely people will have your wrong mappings stored. Other things to point out, DNS redundancy is highly important in DNS. As you saw in the examples I showed you, everything is replicated, right? You must replicate because you simply cannot afford your authoritative name server or any part of that ecosystem to go down. So a minimum is 2. Most services will have 4, 5, 6 replicas, many more, right? Now, all the queries and responses that you saw are normally sent over UDP. DNS does support TCP, but as you saw, the process is simple, right? You're sending one query, you're getting back one response. So the effort of setting up TCP connections is just too much. And imagine the root server having to set up and manage TCP connections for billions of entries, right? So particularly at the higher hierarchy, TCP is probably disabled. They probably don't want to use that. So most DNS clients would just use UDP. You might say, okay, what happens if the query gets lost? Well, the client just retries, right? It sends a query, it never gets a response, it will just retry. So that's fairly straightforward to do because it's just a simple query that you're sending. You could try our alternate servers. So there's various heuristics the clients could use because there's redundancy. If you don't get a response, you could try a different server and so on and so forth. And the port number used is 53, right? So earlier I talked about CNAMEs and I mentioned how CDNs use that, and we'll talk about CDNs a little later, but this is a quick example of a CDN hosted website. So the MIT domain, as you see here, I sent a query for the web domain for MIT and look what I got, right? So you'll notice the first 2 entries, these are effectively CNAMEs. And if I look here in the name, that gives me a hint. Akamai is a very well-known CDN provider. So this is telling me the MIT domain is actually managed by Akamai, right? So this is a very common way to sort of redirect your hosting to a CDN. In fact, even UNSW does that. So here down here, for example, you see all the name servers for Akamai, the IP addresses for them, and so on and so forth, right? Let me just do a quick, demonstration here. So our domains are also hosted, as you see here. So we've probably, I don't know if, does Adobe do CDN hosting? I'm not sure. The name servers are hosted by AWS. I think Adobe does some content management system. Maybe the backend is still AWS, I'm not sure. It's very likely going to be hosted by AWS. But here again, you see another example, right? You'll find this is very common. So CNN, for example, is hosted by Fastly. So most common domains would be hosted by these CDN providers, right? Okay, yeah, one point. This is again something that comes up, dub versus non-dub domains, right? So, I mean, should you be hosting, I mean, basically you have, say, a domain, let's say metalheads.com. Now the question is, how do you manage the hosting for this, right? Do you set up so this is what's referred to as a naked domain or an Apex domain. So that's right at the top in terms of the hierarchy of that naming system. And underneath Metalheads, you could have, say, www, you could have smtp.metalhead.com, you could have ftp.metalhead.com, and so on and so forth, right? Now, till the early 90s, this was not really an issue. You could just have all these different entries potentially point to the same IP address, right? However, with search engine optimization, like Google, for example, they now insist, I mean, they're going to record these domains separately, the way they manage domains. So what this effectively means is whenever you're setting up and managing a particular domain, you generally need to indicate what's your primary domain, which means all the search engine optimization will work on that domain. And then you can redirect this other domain to the primary domain using HTTP, right? There are certain, now you could do this either way. You could say this, you could say the naked domain is your primary domain and then make this redirect here. But normally the rule of thumb is to use the www domain as your primary domain for search engine optimization and make this one redirect to that. So there are two main reasons. So one has to do with how cookies are managed. Now, don't worry about this. This is something we really haven't covered. So I've certainly listed this and you can look up a bit more about that. But there are some security issues that can crop up with how cookies are managed. But the DNS specific sort of requirement is that when you're creating Apex domains, right? And if you want, say, to create a type A record for an Apex domain, the rule is that you cannot have a CNAME record for that particular, for any particular Apex domain. So an Apex domain must always be a type A record. So you cannot have metalhead.com CNAME. That's not allowed according to the way DNS, the standard is set up, right? So what that means is if ever you wanted to outsource your hosting to a CDN provider or some other web hosting facility, you cannot use your Apex domain because you cannot, basically you would need a CNAME entry in order to do that. And you cannot do that on your Apex domain. So typically you'll always find that people will, web domain administrators will use the www domain as their primary domain. And this Apex domain will just be redirected. So they'll just host a very simple web server here. And this web server will redirect you using HTTP if you try to access it and point you to the actual web server, this one. And then that will resolve in a CNAME query, which will point you back to the CDN, right? In fact, we could quickly look this up. So we've already seen so let me do a query for the non-Apex domain. Apex and primary are the same. These are just two different words. I mean, not strictly. Apex is this, what I showed you. Now the question is whether you want to use the Apex domain or the www domain for your SEO optimization, because SEOs treat one domain as the primary domain where they're going to do all the sort of optimization, right? So here, for example, if I did just a Apex domain query for UNSW, you'll see that it's giving me this particular IP address. Now it's very likely what's happened is they've set up a very simple web server here. And if I try to send a HTTP query for the UNSW domain to that web server, it's going to redirect me to the other one that I showed you. Right, so it's going to redirect me basically to the www domain, which will point me to that particular CNAME. So if you want, we could quickly send a query to 202. Let me just note this down. 58.60.194. So this is a web sniffer. Websniffer.cc. So here you can actually sniff the queries, the HTTP response headers, basically. So let me, or maybe let me do this. Let me just send it to, or maybe directly that address. So 202. Oops, sorry. CAPTCHA. I hate CAPTCHAs. What am I looking for? Planes. Okay, we are back. Now let me just try the HTTP one. Right, so I'm sending a query to that one that you saw. Okay, yeah. So you notice the response I got back. So this generated a GET request, right, for that particular to that particular domain, the 202 whatever. And you notice here it's telling me the website has permanently moved, right? So 301. So if I send it here, then you're going to get the actual. Yeah, so you notice now I have the actual page that I wanted, right? So that's how all of this basically works, right? So yeah, certainly if you're interested, have a look further here and you can do a bit of investigation on your own. Now, certainly CDN providers do have some workaround, so it may be possible to still use your Apex domain as your primary domain and get around this. But again, that takes us into the deep end of stuff that we don't really have time for in this course. So is there a way to determine the boundary? So as I said, generally the rule of thumb, and as you saw even with UNSW, is to use that particular domain as your primary domain. And then if someone tries to access this, you just redirect back here, right? That's generally the rule of thumb. Okay, a few other things before we wrap up. So there's this whole issue of using your local DNS server, right? Now remember, this means any websites that you access, you need to send a DNS query, right? And which means your local DNS server effectively knows all the websites you're trying to access, because all the DNS queries go to your local DNS server. Now, which also means your local DNS server may block if it's trying to do some censorship, it may block certain websites. So you might want to, you send a DNS query for a particular website, your local DNS server will never send out the query into the DNS hierarchy. It will just say bad query or whatever, right? So this means your local DNS server has a lot of power. Effectively, it's tracking all your queries. It can also block certain queries if it wants to censor you. So there are certain issues around that. I mean, in general, to get around that, people sometimes like to use these external DNS servers like Google. There's a bunch others that you can use out there. There's some that are recommended by the EFF, the organization that's effectively trying to prevent censorship and so on and so forth. However, again, if your ISP is being really bad about it, they may block even these DNS queries that are going out to these sort of widely known public DNS servers, right? So again, I don't want to get into all these legal issues here, but just making you aware that there are some issues around this, because this can be a potential issue when it comes to censorship. DNS security. Okay, so yeah, there's some issues around this denial of service attacks. So for example, what if you start bombarding the root DNS server, right? And you try to bring it down. Now, normally root DNS servers are well managed. They use all sorts of traffic filtering mechanisms to avoid these sort of denial of service attacks. Even the TLDs these days are, they're a lot more careful. So it's very hard to actually bring down the root DNS server and the TLD servers. There are some other attacks you could launch, like you could send bad DNS responses. So this is what's referred to as DNS poisoning, where you sort of send bad information and corrupt someone, the entries that are cached, and that can potentially redirect people to websites which look like the websites you're trying to access, but they're really not. And I'll show you an example on this. I think we'll have to do it on Wednesday. I think that's on the next slide. And then there are certain sort of attacks where you might essentially send a lot of DNS queries claiming they came from a particular address, which will result in a lot of responses going back to that victim's address. So this is a sort of what's called a Smurf attack or an amplification attack, where you're targeting a particular victim by sending a lot of fake queries claiming to come from their IP address, and then they get all these responses back. So yeah, there are certain issues, security issues around DNS, and there are certainly standards to get around that. So there's this whole layer of security that's overlaid on top of DNS, which addresses that. But we'll leave it at that. So I think I may stop here. I'll quickly wrap up this poisoning bit, and then we'll look at some of these quizzes when we meet on Wednesday. So yeah, have a great week, and we'll all reconvene on Wednesday. There's a question: if we run our own servers, should we worry about DDoS attacks? Generally, yes. Whenever you're setting up your own servers, you do need to be careful about DDoS attacks, right? So typically, if you're setting up servers, you would be using some sort of firewall or security systems, which will try to protect your servers from denial of service. Okay, so have a great week, everyone. Do remember your labs are due tomorrow, and I'll see you all online on Wednesday. Bye-bye.